My name is Radostin, and I'm a PhD student at the University of Oxford, and today will be presenting our work on enabling secure container checkpointing for distributed model training. So this work is in collaboration with Victoria, Maniz, Adrian, and my supervisors, Professor Rodrigo Bruno and Professor Wes Armo. So just a brief background. So this is kind of summarizing my PhD over the past few years. So there are three main topics that we'll cover later on. But the main motivation for this work is that with the increased adoption of AI workloads, the size of models is continuously increasing, and these models are trained on larger and larger clusters. And essentially, with the increased scale, these workloads experience a larger number of failures, and handling these failures is becoming crucial. Recent publication from Microsoft was showing that essentially this type of errors can cost a few $1 million per month, essentially because GPUs are very expensive and wasting GPU computation time is a significant problem for many people. So the technique for handling errors that is used both in HPC and cloud computing is called checkpointing. And with the increased model size, implementing efficient checkpointing mechanism is becoming more and more important, because inefficient checkpointing can lead to low GPU utilization. So there are two main checkpointing methods. The first one is widely used, for example, at application level. For example, with PyTorch, you can create what is called model checkpoint that can be later distributed and used to essentially resume the, for example, inference. And what we focus on is a different type of checkpointing called infrastructure level checkpointing, where, for example, we can create a checkpoint of any application without modifying the code of the application. And this is mainly used at cluster level. For example, if you have an operator that performs maintenance of a cluster node and need to move workloads from one node to another, this type of checkpointing mechanism becomes very useful. So one of the challenges with enabling this transparent checkpointing mechanism is saving the state and restoring the state of GPUs, mainly because GPU drivers are proprietary, and essentially understanding the GPU architecture versus CPU architecture is very difficult. So over the past 2-3 years, there's a team at AMD and NVIDIA that essentially extended the GPU driver to have capabilities that allow us to checkpoint and restore the GPU state. In particular, with NVIDIA, they introduced a tool called CUDA checkpoint. This tool allows you to essentially capture the GPU state and move it into host memory. And then we have another tool called CRIU, checkpoint restore in user space, that allows you to save essentially the memory pages and the host state of the container. So this tool is integrated with several different container runtimes, including Docker, Podman, and Kubernetes. The other challenge with checkpointing training workloads is that they're distributed. While the CUDA checkpoint tool is very useful, it is implemented at low level, where it handles a single process. So when we want to checkpoint a distributed computation, we need to essentially synchronize this checkpointing mechanism. So we introduced a new tool called CRIU coordinator. This tool allows you to essentially synchronize the checkpoint and restore operations across multiple instances. For example, if you want to checkpoint multiple containers that are distributed across multiple nodes. And the last challenge with checkpointing distributed training workloads is that they can be training on proprietary data or sensitive data. And when you create a checkpoint, essentially you're capturing the memory pages of this application, and you don't really want to expose this to essentially untrusted users. So implementing encryption is very important, and the two common approaches for doing that is using the standard encryption tools where you create a checkpoint and then you read this checkpoint back and encrypt it and then save it again. But this introduces a lot of overhead because, for example, if you have hundreds of gigabytes that you have to read and then write back, it takes a lot of time. And the other approach is called checkpoint streaming, where it's commonly used with spot instances. For example, when you have limited amount of time to create a checkpoint and you want to avoid intermediate storage by directly streaming the checkpoint to a remote server. And this pipelining mechanism essentially allows you to encrypt the data. But again, it's difficult to integrate with, for example, Kubernetes. So what we did is we extended CRIU to support checkpointing. So essentially, we implement the encryption mechanism within the checkpointing to CRIU. And this allows us to encrypt the data before it is written to disk, and then to decrypt it back during the restore operation. So this is what we call end-to-end encryption, where we essentially we encrypt the data before it is safe to local disk. And the challenge with implementing this is that you have different types of images, what we call CRIU images in the checkpoint. So this could be, for example, the state of processes like open file descriptors, TCP connections. And essentially encrypting this data, we use a stream cipher. And we have a different type of data, for example, memory pages, where you have blocks of data that have fixed size. So in this case, we use block, essentially AES, more efficient way of encrypting the data. So I have a short demo here. This is essentially how you can use checkpoint restore coordination with a distributed training job. So in this case, we have two instances of Torch, of PyTorch. And in this case, we so once we create the both containers, we can essentially generate a configuration file that is used to synchronize the checkpoint operation. And then essentially you can use the checkpoint restore functionality of container engines to essentially perform the checkpoint restore operation. And the CRIU coordinator has a client and server side. The server side is essentially performing the synchronization of different operations. You can see on the top side. But essentially, it's how we can enable transparent checkpoint restore of distributed workloads in GPU clusters. So we evaluated these mechanisms with different models, and we can see that checkpointing takes a few seconds for different models, and restore is always faster. So this is very helpful with what we call hot swapping. For example, you can skip the initialization phase of inference workloads and essentially serve larger number of models on fewer GPUs. And we also evaluated the encryption mechanism and compared this with other tools like GNU-PG and OpenSSL, and we can see that it's more efficient. It's mainly because we can skip the I/O overhead of reading and writing a checkpoint. And we are currently in the process of setting up a checkpoint restore working group in the Kubernetes community, and we plan to continue essentially the development of this work. A few people from the Kubeflow community reached out to us, and we are currently working with them on essentially enabling this functionality in Kubeflow. And thank you very much. If you, yeah, I'll be happy to answer any questions. Okay. Yeah.
I have a question. Would you help to understand better the CUDA checkpoint and the CRIU project?
Yeah. So it. can just go back here. So the CRIU project has what we call plugin mechanism. So it allows us to extend CRIU with, for example, handling of unique file descriptors. So for example, if you have specific file descriptor that you want to checkpoint to the GPU driver. And this plugin mechanism is just a library, and this library calls the CUDA checkpoint tool you can see here. So CUDA checkpoint is a separate GitHub repository under the NVIDIA organization, and you can just use it on its own, but it's just checkpointing the GPU state. CRIU handles essentially the CPU state. And we have something similar for AMD. For AMD, it's slightly different. So it's actually using the IUCTO kernel APIs to perform the checkpoint restore operations. Yeah.
We're on the same side off topic, but do you know of any container runtime checkpointing as well via CRIU plugin?
Yeah, so it's completely transparent. So currently CRIU is integrated with Docker, Podman, CRIU, Containerd, so you can use it with Kubernetes. And essentially the plugin mechanism is part of CRIU, so you can just install it. I'm also package maintainer for the plugins in Fedora, so you can just install them. Yeah.
Technical sense, related. So the plugin is by the file descriptor type, like the prefix, or?
Yeah, it's kind of interesting. So we identify, it's not only file descriptors, it's also virtual memory areas and a few other things. But essentially, it handles things that we don't know how to checkpoint. So for example, we identify the type of the file descriptor.
By the name of the symlink, of the magic symlink?
No, I have double check in the source code, but essentially it's using some kernel API call. Like we can obtain a list of all, when you do LS on the proc file system, you can see information about different type descriptors. So if it is the device file descriptor, then we need to use a plugin essentially to checkpoint and restore it. So this is similar with InfiniBunch is one of the challenges we had in the past, so we had to implement special support for checkpointing. Network devices is kind of the same thing. When you're checkpointing container, you want to checkpoint restore network devices. But essentially, we identify the type of what type of file it is, and then we use different mechanism for checkpointing and restoring it. And we can't really do this with GPUs because we don't know essentially how the driver works. And this is where the AMD and NVIDIA teams helped. Okay, thank you. Thank you very much.